What do physicists and eye doctors have in common? They both make use of the Michelson interferometer to make sense of the world around them. Physicists use this to understand the nature of light, study what light is made of, and how it interacts with itself. Eye doctors, on the other hand, use this technology to image the retina. This is done using what is called optical coherence tomography, or OCT for short. OCT has been crucial in making early diagnoses to prevent vision impairments. So without further ado, let's take a look at what this interferometer is all about.
This is a bird's eye view of a Michelson interferometer. We have a monochromatic light source, which is usually a laser, to input light into our system. We'll be using a green laser in this case. When the laser is turned on, a beam of light will travel out towards this beam splitter as such. A beam splitter is a really interesting component. It's simply a glass prism which is capable of splitting one light beam into two beams. Therefore, when our beam reaches the beam splitter, some of the light will continue to pass right through, and some will be split off and change direction. To keep track of these separate light beams, I'll draw them in different color. But note that this does not mean that our light has changed color, it's still just green light. The light beam would change direction will be met by a mirror, let's call it M1. When it reaches this mirror, it will reflect and travel back towards our beam splitter and continue straight through to our screen. The same thing happens with our beam, which didn't change direction and travels straight towards our mirror, let's call it M2. It will also reflect off the mirror and travel back towards the beam splitter, where it will be reflected this time and change direction, traveling towards our screen. So now we see that the beam, which we originally split, has been recombined and travels towards a blank screen. So let's recap. We send one light beam into our device, which is then split, with one beam traveling to mirror M1 and back towards the screen, and another traveling to mirror M2 and back towards the screen.
So what's this fuss all about? Why do we do all this sorcery to split one beam of light into two, only to recombine them at the end and view it on a screen? In order to understand this, we have to think of light not as a straight beam, but as a wave. So now we'll take a little detour and look at the wave superposition principle to see how this works.
The wave superposition principle sounds a lot more complicated than it really is. All it means is this. I can have two waves existing in the same region of space. The amplitude of these waves add linearly, so let's plot their sum down here. This purple wave is equal to the orange plus the blue wave. As I shift the waves relative to each other, the sum changes based on how the waves align. If I shift them such that the peaks align with peaks and valleys align with valleys, we get a wave that is twice the size of the original waves. We call this constructive interference. If I shift the waves so that the peaks of one wave align with the valleys of the other, they cancel out and we get an amplitude of 0. The waves seem to disappear. This is called destructive interference. The bottom line is this. If we set up our interferometer such that the two beams arriving at the screen are perfectly in phase, then they interfere constructively with each other and we see light at the screen. However, if the waves arrive at the screen when they are perfectly out of phase with each other, they will destructively interfere and we won't see any light on the screen. Now without further ado, let's hop into the lab and fire the interferometer up. Here is our typical interferometer setup. This is the laser which will be the source of light into our system. When this laser is turned on, light will travel out of it towards this beam splitter. We see that our beam splitter has its axis along this diagonal line. As a result, when light reaches it, half of it will be split to this mirror M1 and half to mirror M2. Light will then reflect off of these mirrors and travel back towards the beam splitter. From there, it will travel towards the screen and cause our interference pattern. I can now turn our light on, and you see that once it is turned on, we see an interference pattern on the screen. Here I have a knob which allows me to move the mirror backwards and forwards on the micrometer scale. This allows us to make changes small enough for us to observe. Using this knob, we could change how the light waves align with each other, and therefore we can see changes in the interference pattern. Let's turn the ambient lights off and zoom into our screen to get a better look at our interference pattern. We see a hypnotizing concentric pattern of light. We call these bright and dark areas fringes. For the sake of simplification, we'll ignore the outer fringes for now and focus only on the central spot. We see that right now, this spot is bright. What does that tell you about our current setup? Well, going back to wave superposition, this means that the recombined waves are perfectly in phase. This tells us that the distance from the beam splitter to mirror M1, let's call it length L1, is equal to the distance from the beam splitter to mirror M2, we'll call it length L2. Since L1 equals L2, both beams of light will travel the exact same distance through the interferometer, which means that when they reach the screen, they will be perfectly in phase. Their peaks will align, and we therefore see a bright central spot. Now, let me ask you a question. What if I use the knob to move mirror M2 back a little bit? What do you expect will happen? Well, let's draw it out. So, if this mirror moves back, then the wave traveling to it will have to travel a longer distance through the interferometer than the wave reflected from mirror M1. So, if this is how the mirror M1 wave looks when it reaches the screen, the mirror M2 wave will lag slightly behind it. If it lags enough that the wave becomes completely out of phase, the superposition principle tells us that the waves will cancel out to be zero. So what do you expect to see on the screen? Alright, now that we've made our prediction, let's try it out. I'll use the knob to move mirror M2 back, and we see that I end up with a dark central spot on the screen. The setup tells us that the waves are perfectly out of phase and therefore cancel out to be zero. I can also continue to rotate the knob, and you'll notice that the central spot continues to vary between bright and dark. This is because as I move the mirror back, we keep getting times when the waves are perfectly in phase and other times when they are completely out of phase. I think that's enough sorcery in the lab for today. Let's talk about some applications.
How the Michelson interferometer came to be is a really interesting story. In short, it was put together by two scientists in the 1880s to detect the presence of the ether. The ether is a medium that physicists used to believe light waves used to travel through. The experiment did not show presence of the ether, however it did tell us that light travels at a constant speed in all directions. Now, other than discovering the deepest mysteries of the universe, what can we use this technology for? This is where eye doctors come in. Optical coherence tomography, as we mentioned previously, is based on the Michelson interferometer. It allows us to take images like this. It's so precise that we can identify and label all the layers of the retina. This is super useful as we can detect many diseases and conditions such as retinal detachment, retinal holes, and subretinal fluid. And the list goes on. Understanding how OCT machines work is a video for another day, but since we're already here, I'll do a quick demo.
What if we remove this mirror and place someone's eyes here instead? I'll draw in different colors to represent the different retinal layers. Let's move mirror M1 so that L1 is equal to the distance from the beam splitter to the first retinal layer. If I send in a quick laser pulse, only the light reflecting from the first retinal layer will arrive at the detector at the same time as the one reflected off mirror 1. In this way, we can detect the first retinal layer. Now, let's move mirror M1 back again so that L1 is equal to the distance from the beam splitter to the third or the yellow retinal layer in this case. We can send in another quick laser pulse. Light which reflects off the first or pink retinal layer in this case will arrive at the screen before the one which reflects off mirror M1. As a result, we will not see an interference pattern. The same is true for the light which reflects off the blue or the second retinal layer. However, light which reflects off the third retinal layer will arrive at the screen at the same time as the light which reflects off of M1. This is because L1 is equal to the distance of L2. As a result, we will see an interference pattern and can detect the retinal layer. We can keep sweeping mirror M1 backwards and forwards across all the different retinal layers in order to formulate an image of the whole retina. That is a very, very shallow introduction into the topic, but it should be enough to get the idea across.
Wow, we've been through one heck of a ride. We talked about wave superposition, the interference of light, the Michelson interferometer, and some of its applications in history. Thank you so much for watching this video. I really hope you've learned something new today and gained something from watching. I love sharing scientific concepts and ideas with the general public. This was a very dense topic, and so I skimmed over a lot of things and simplified a lot of things. If you do feel that I simplified things a bit too much, or if there's something that you didn't understand, please feel free to reach out to me. I would love to clarify. Thanks again for watching, and I'll see you next time.